talking about the syllabus. No one's ever gonna watch that ever again. Let's see. Yeah, so I'll start talking about the syllabus, and I'll kind of go between, I guess, the tablet and Canvas as well. One second here. I'm still getting used to how technology works at the beginning of this semester. So yeah, I don't really have that much to say from the syllabus. It should probably take like 20 minutes, but sometimes I yap a lot more than I should. And so I'm not gonna pass out the syllabus. I didn't want to waste the paper. Like I'll print out the notes and pass out the notes, but I'm not gonna, print off the syllabus and send it to everyone when you can just find it online. And so I think the main thing to focus on in the syllabus is going to be what the grading scheme is going to look like. But before doing that, some additional information. So obviously my name's Cody Gilbert. There are going to be office hours this semester. I usually have 5 office hours, but I don't decide them until after a classroom pool. So sometime during this week, I'll send you a link where you can participate and choose the hours of office hours that work for you. I choose the hours that work for the most amount of people. And so I try and squeeze in an hour that works, or at least 5 hours that works for everyone that participates. Sometimes that's impossible, in which case you can just email me if you ever want to meet. Otherwise, you can just find me in one of those office hours. So I'll send out an announcement later this week regarding office hours. My office itself is in Ritter Hall 137. It's just 2 floors down from here, pretty much, like directly 2 floors down, just on the other side of the hallway. And then my email is cody.gilbert@slu.edu. So if you have any questions about the homework of the class, this is probably the first place you want to go to, is just email me and ask that question. I'll try and respond in a somewhat quick manner. And so, yeah, so course description. So the focus on linear algebra is, how do I sell this? So I would say like linear algebra, I think is probably the most important math in the modern world, more so than calculus. Of course, like sometimes you use calculus when you're doing linear algebra if you want to measure some sorts of like rate of change or something like that. But really, the digital world and a lot of digital technology is an offspring of linear algebra. In particular, neural networks are obviously important today. Machine learning is an important area of study. Neural networks in machine learning is just linear algebra. Like if you know about like a feed forward network or back propagation, it's really just matrix multiplication for the most part. I mean, there's a little bit more to it than that, but at the end of the day, you're just multiplying matrices and messing with matrices, which is the realm of linear algebra, right? Even on writing in this tablet or writing on this tablet, like so, if I were to take this little squiggle I drew and I translated it somewhere else, I'm technically performing what's called a linear transformation. Or if I'm shrinking it down, I'm scaling it by some sort of scalar. So in doing this, I'm doing linear algebra, or at least that's what's underneath the hood of a lot of this technology. And so we're going to be looking at linear algebra and how it's used in, and this isn't linear algebra for engineering, but I still want to look at applications in engineering, machine learning, maybe some economics and statistics as well. And so I'll say more about what we're going to be doing in this class as we move forward. So I talked about the textbook already. It's online on Canvas. You don't have to buy it. The grading scheme is going to look something like this. And so I guess I would partition the assignments in 2 different categories. So the first category is attendance, participation, quizzes, and homework. These are points. I don't want to use the word like free when talking about these points, but as long as you put in the time into this class, I think these points should come to you pretty easily. It's 40% of your grade. And then the part that's going to be a little bit more difficult are going to come from exams. And so in this class, there's going to be 4 exams. I usually do 3 exams, but I think 4 exams works more naturally here. And it makes it so the exams aren't as consequential. So if you do poorly on one exam, it's not going to like nuke your grade or anything like that. But the exams is really just where you're demonstrating your understanding for the course. My exams usually aren't too terrible, in the sense that both for calculus and linear algebra classes I've taught in the past, I think the averages are usually between like an 80 and an 83%. So I try not to make it so like everyone fails the exam or anything like that. There's usually like a good mix of like easy problems, medium problems, and then maybe like one or two harder problems. So usually exams aren't too severe in this class. I'll talk more about exams when the first one approaches about a month from now. I'm trying to remember. Okay. Yeah, attendance and participation is pretty much free, I would say. I would say attendance and participation, it's not going to hurt you in any way for the most part. It's mostly just a way for me to justify rounding up your grade at the end of the semester. Like if you have like a 79% or something like that, and I'm like, well, this person went to class pretty frequently. They asked questions. I felt like they had like an active role in the class. Like it gives me a justification to give you a B minus instead of a C plus, pretty much. Or if you do really well, maybe you can go from like an 81 to an 83% in participation if I feel like you go above and beyond. But this isn't really to hurt your grade in any way. I'm not going to be keeping attendance. So, like, whether or not you show up to class is up to you. And I'm not going to take off points if you don't attend class. Again, I'm going to be recording all of the lectures. So, I mean, if you learn better by watching the videos, you can just watch the videos. I won't be offended or anything like that. The only way you can really lose points with attendance is if I feel like you're being disruptive in class or if you're insulting other students or something like that, which has never been a problem in the past. But I guess that's the only way in which it gives me a way in which I can penalize you if I feel like you're being a nuisance to others. Which I mean, as long as you employ common sense, it shouldn't be an issue. It's never been an issue in the past. Quizzes. I'm kind of talking off the top of my dome here. There's going to be weekly quizzes. Not this Friday because I don't like having quizzes on the first week. I think with quizzes, it's going to work kind of like group works did in my calc classes. It doesn't say this on the syllabus. I just say like a quiz, but it's probably going to be like a group quiz or something like that. Again, I kind of want the quizzes to be like an easy part of the grade. So it'll probably be like the first 20 minutes on Friday's classes. I'm going to go over some new material. And then the last 30 minutes, I'll give you like a quiz in which you can work with others on it or something like that. And you can also ask me questions. So it'll probably be more like a group work than a quiz. But I'll say more about it when the first quiz is staring us down, I suppose. Instead of saying it now and then everyone forgetting about it and then re-explaining it 2 weeks from now or a week and a half from now. Now, homework, I feel like there's something to say about homework. So the homework, it's not going to be online. I haven't posted the first homework yet, but I'll post a PDF on Canvas that's going to have maybe like 7 or 8 problems on it, and it'll be due sometime next week. Actually, the first homework is going to be due on the 26th, so you'll have 2 weeks for it rather than just a single week, because I don't like having homework due at the end of the first week or after what was covered in the first week. With the homework, I feel like homework nowadays is kind of like free in the sense that you can put it into like ChatGPT or something like that, and it's probably going to give you the right answer. Maybe ChatGPT is like deteriorating in quality a little bit, but I still feel like it will be able to give you the right answers to like any linear algebra problem pretty much. So I'm not like innately against ChatGPT. I think there's a right way of using it. The wrong way of using it is just copying down what it says without thinking about it or even like contemplating like why it's doing what it's doing. In which case, like you're not really preparing yourself to perform well on the exam. It's kind of the big problem. But I mean, when I was a student, we still had like Google, and I feel like Google had the exact same purpose, where you can just look up things on Google and you can still find explanations. The big point was you actually write down and think about what it's saying rather than just mindlessly copying it down. The main point in the homework assignments is to make sure you understand how to do the exam problems pretty much. I usually choose exam problems that are similar to what we covered in class in the notes, as well as what's going to be on the homework as well. And in general, I try and make it so the exams are pretty predictable. Another purpose of the homework is to kind of build up muscle memory. When you're actually doing the exams, you shouldn't actually be doing that much thinking. A lot of it should just be like, I remember how to do this from like other problems. Like it's kind of like muscle memory a little bit. Like if you do like row reduction 10 times, then when I do ask you to do row reduction on the exam, it should be like pretty straightforward. Or it's kind of like derivatives. If you do like 100 derivatives, like you don't really think that much about doing like the 101st derivative. That's kind of the purpose of homework. is to put in like that muscle memory. But if you're not thinking about the problems or you have like ChatGPT do it for you, you're not really developing those skills to do well on the exam. So, I mean, I'm not going to bar you from doing ChatGPT on the homeworks or anything like that. I think it is a valuable resource, but you just need to make sure that you're actually learning if you're using it, right? So, I think like how I would suggest doing homework problems is to give it a good try and think about it on your own. If you get stuck, you can use like ChatGPT or something like that. I think that's a good way of going about things. Is there, let's see, I feel like I've said what I wanted to say about quizzes and homeworks. Is there anything from this I want to say? I think I said everything I want to say about quizzes. I guess in terms of lateness with homeworks, there'll be a 5% flat penalty for each day that it's going to be overdue. So homeworks will generally be due on Mondays. So if you turn it in on Tuesday, it'll be like a 95% out of 100. 2 days late would be a 90%. 3 days late would be an 85%. And probably do the math. And yeah, that's pretty much it for that. Exams. Again, there's going to be 4 exams. There's 3 midterms and a final. But the final exam is also worth 15%, just like all the other midterms. So the final exam is actually the nicest midterm in the sense that it's going to be as long as the other midterms and worth as much as the other midterms, except you have 2 hours to do it instead of 50 minutes, pretty much. So I don't know. I don't think that's like too big of a problem or anything like that. But yeah, the final exam is worth just as much as the other midterms. I'm not sure if I'm going to make it cumulative or not. It's going to depend on whether or not I think there's enough material covered by the end of the last couple of units of the semester, pretty much. This is months away, so no one really cares about that at the moment. But this is the schedule. They're all on Fridays throughout the semester, pretty much. Office hours, I already talked about. Course objectives, just to learn about linear algebra. I feel like that condenses that. What else? I already said attendance. I'm not going to keep track of attendance in this class. I will say that students that attend class generally do better than students that don't attend class. I got a question.
Are you gonna be like a G and we'll just have a note card on the test like you used to, or are you just gonna
I like that you
and like go through?
I like that you threw it in like you used to. I mean, yeah, you can probably.
I mean, maybe you're feeling art. Just gonna like screw us over.
Wow, that's like I feel like you're poisoning the well and framing it that way a little bit. But I mean, I am planning on allowing you to use cards or a note card on the exam. But that could change. Assuming the behavior is good. Okay. But I plan on allowing you to use like a note card. I allow it on all my classes.
The maximum size of the note card thing.
Whatever the normal size of a note card is. I think it's like 3x5 or something.
Yeah.
I would imagine inches. We're in America. We don't do meters, we do inches. Yeah, attendance again, I don't really I'm not gonna keep track of attendance, but those that attend usually perform better. Really the only peril there is in this class, I would say, is if you fall behind in keeping up with the new content that we're going over. Like if there's an exam coming up and you're behind on like 10 of the lectures, that means you're going to be cramming for like 10 lessons or doing like 10 sections in 1 week, whereas the other students are working on the exam review, which means that you're at a disadvantage compared to everybody else. So the best way of keeping up with the material and making sure things don't snowball out of control is just attending class and at least familiarizing yourself with what's important. And usually during class anyways, I kind of say what's important and what might show up on the exam and what might not show up on the exam. So I try to make it so the exams are predictable based on what we cover on in class. So if you attend class, you kind of already know what's going to be on the exam beforehand, I would say. So that's what I have to say about attendance. I can make changes to the syllabus. I kind of already talked about technology and AI. You shouldn't really need calculators in this class. On the exams, I'll allow you a scientific calculator, but I'm going to keep the numbers pretty small. It's just kind of there if you need to check your answers, I suppose. But you can do it without the calculator and it should be fine as well. Yeah, that's pretty much everything. Everything else you can It's kind of boilerplate, like it shows up on every syllabus, so I feel like I don't need to say anything. I also posted the following calendar. If you want to see what we're covering on what day throughout the semester, this is the schedule I'm going to try and follow. It's here. I guess I can pull it up. So if you go on Canvas, it's in this tentative schedule underneath the course syllabus as well. This is more for me than it is for you. I actually don't know why you would care to see this, to be completely honest, but in case you're curious about what the semester looks like, it looks something like this. So these are the days before like the first exam, and then the first exam is on the 13th. Oh, and I should also mention, just like my calc classes, we're going to dedicate one day to exam review. So the first week, we don't have class on Wednesday due to a wellness day. So on Monday, there's going to be the exam review, which is just going to be me going over problems I send out as part of a review. Then on Friday, you'll have the exam. So there'll be at least one day dedicated to reviewing for the exam. If we finish the content a little bit early, maybe it might be like 2 days or like a day and a half or something like that. Okay, I think that's everything that I want to say about the syllabus. Honestly, I don't think I have that much more to say. Before I go on, are there any questions about the class or the syllabus at this point? Yeah.
Or is homework today?
It would just be turned in person, I would say. I mean, maybe. Well, that's what I would say. I mean, maybe you can do like a scanning thing. I haven't set up. There's like a application people use. It's like GradeScope. I thought about setting up GradeScope. I haven't tried it yet, but I was just gonna say you just write it out on paper and you turn it in during class, or you can like slide it under the door of my office or something like that.
That suits me, thank you.
Mm-hmm. Yeah, any other questions? Yeah, and then the only other thing, I don't remember if I said this or not, but everything you need to find for this class is under the module section for like the Canvas page. So you can find the syllabus here, schedule, the textbook. Then every week I'm going to post the weekly overview. This is how you'll see it as a student. So I have a couple of things blocked out, but you'll see under week 1, under this link, you'll be able to find the notes that I'm going to be covering for the week in case you want to follow via tablet in class instead of on paper. You can find the empty notes here. So you'll click on this, they'll show up, and these are the notes I'm going to follow. So we'll fill in like these various examples in class. And usually there's homework assignments that'll be written here too, but there isn't going to be a homework assignment that's due until the 26th. So we'll worry about that next week pretty much. And I think that's everything. The lecture notes are here as well. And then when I'm done recording lectures, they're not here yet because I haven't recorded any lectures. It'll be underneath the lecture notes. And then by the end of the week, I'll post solutions to the lecture notes as well. So I usually post solutions to pretty much everything we do in class. Any last questions before going over the content? Okay. Just give me 1 second. Yeah, so we're going to, I feel like the first week is really just a review of things that we've already covered in Calculus 3. So Calculus 3 is a prerequisite to this class, so I kind of expect everyone to know pretty much everything that we're covering the first week. It's fine if you haven't seen some things, but some of this stuff I just copied directly from my Calculus notes. It should be pretty familiar. So every week, I'll be printing off these notes that tasking out like I am now. This isn't just like a 1 week thing or anything like that. So these notes are the main way of keeping track of what's going on throughout the semester. Usually when I'm writing the exams, I think about what was covered in these notes and determining whether or not like a problem is appropriate or whether or not it's not appropriate. Did everyone get a copy of the notes? An extra. I can collect that. Yeah, so maybe the first week I mean, it should be a little bit boring and that you've probably seen all of these things before in Calculus 3, but I need to remind you of it because it's the foundation of linear algebra. So at its most base level, linear algebra is a branch of mathematics that focuses on studying vectors, vector spaces, which can be thought about as the home of vectors or where vectors live. It's the study of linear transformations, which is how to transform vectors via linear functions. And then it also focuses on solving systems of linear equations, which is pretty much how to perform algebra with vectors. So the main thing I'm trying to point at here is that all of these concepts that I'm mentioning involve the word vectors in some capacity. So vectors, or the study of vectors, is really the foundation of linear algebra. And so the first thing we're going to talk about this semester is going to be vectors and then linear combinations of vectors. And so the first question is going to be, what is a vector? And I think the unintuitive way of defining what a vector is by just saying that it's some sort of mathematical quantity that has both a magnitude and a direction. That is to say, it's something that has some size or length, and then it points in a specific direction. So you can think about direction as being some sort of angle with maybe like the x-axis or something like that if you're working in R2 or in 2 space. And so this isn't really the most intuitive way of thinking about a vector. Generally, when we want to think about a vector, it's something we want to be able to visualize. And so you can think about a vector visually as really just an arrow that goes between two different points. And so that's what's represented here. So we have an arrow that's starting at some tail, which is like this point here. Like we're supposing, we aren't even necessarily in 2 space or anything like that, but we're starting at some point here that serves as a tail, and then it terminates at this head here. And in drawing this arrow between the 2 different points, the tail and the head, we're going to have an arrow that has a magnitude, i.e. a length, and it's also going to have a direction as well. That's defined by these 2 points. And so upon drawing the arrow between the 2 points, the direction is then going to be clear. And then the magnitude is just represented as the distance between the 2 points. So you can use the Pythagorean theorem to determine what the length of the arrow is going to be, which I'll say more about later on. And so a vector with tail P and a head Q is going to be denoted in the following way. So it's PQ with an arrow over top of it, which is hopefully pretty intuitive. And so while this is intuitive visually in terms of like what a vector looks like and what it represents, it is a little bit unintuitive in the sense that the points P and Q don't really matter necessarily when we think about defining a vector. In fact, the points P and Q don't matter at all for the most part, which will be clear after we look at the next page. And so this is a more formal way of drawing a vector here. We have a point P and a point Q, and then we have the arrow that goes between these 2 points. If you go on the next page, however, at the top, you'll see that all 4 of these vectors that we have are the same as one another, despite the fact that their beginning point and their ending point are different. What matters between these various points we have is if I draw this green arrow here and I were to translate it over to any of these other arrows, they have the same angle / direction and they have the same magnitude as well, right? So as I move this arrow around, these vectors are all really the same thing at the end of the day, minus human error. I probably made the arrow a little bit too big, but you get the idea. So all of these vectors are the same as one another because you can translate on top of one another perfectly, right? So in that sense, the beginning point and the end point don't really matter, as long as the magnitude and the direction of the vector is maintained between various points. So that's written here. Turns out all of these vectors are the same. Why? Because they have the same magnitude and the same direction. All that really matters when you're thinking about these vectors or when you're defining these vectors is going to be the change in x and the change in y as we move from P to Q. And so in Calculus 3, this is the notation that I would generally use. So if P is equal to the point x1, y1, and Q is equal to the point x2, y2, then we can write out the vector PQ in the following notation. So we have this bracket notation where the first component reflects the change in x that's occurring. So it's x2 minus x1. And then the second component is the same thing with respect to y. So it's y2 minus y1. So that's what's represented in this picture that we have here. If we wanted to write out this vector u in terms of this bracket notation, it would be 5 minus 2 in the first component, and then it would be 6 minus 4 in the second component. And so this would give you the vector 3, 2. So it's a vector that goes 3 units to the right and then 2 units upwards, which is reflected by this bracket notation here. So this is just saying we're going 3 units to the right, 2 units up, like so. And if we did the exact same thing with this vector w, we would do 12 minus 9 in the first component, and we'll do 6 minus 4 in the second component, which gives you the same vector over again, right? It's just going to be 3, 2. The main thing it's capturing is the change in x that's occurring, which is this 3, and then the change in y that's occurring, which is given by this 2. Right, so even though they're beginning and ending at the same point, it's the same vector at the end of the day. Okay, any questions so far about vectors? Usually it's going to be a little bit more involved in that I'll go through examples and ask for help when going through those examples, but I don't know. Right now I'm just defining the very basics. It's going to be a little bit boring initially. You've probably seen all this already. And so in linear algebra, we're not just going to be concerned with vectors in R2. We're also going to be concerned with vectors in R3 and really beyond as well, right? We're going to be thinking about Rn eventually, which is like arbitrary n space that's technically like n-dimensional, and be doing computations in that realm as well, which maybe you won't be able to visualize, but you can perform algebra that will describe some characteristics. And so in R3, rather than R2, we have 3 directions, and therefore every single vector is going to have 3 components corresponding to an x-axis, y-axis, and then a z-axis as well, which will be visualized in the future. And so we say that 2 vectors are going to be equal to one another if they are the same in every single component. So these 2 vectors are equal if we have that x1 is equal to y1, x2 is equal to y2, and then x3 is equal to y3, like so. And so usually throughout this class, I'm going to denote a vector as v in boldface, or it can be v unbolded, except you have like a little arrow above it as well. So I'm going to go between these. When I'm writing things out, it's probably better that I use this notation because it's, you can't really tell if it's bolded or not if I'm writing, right? But in the notes, this is how you tell. It's going to be like a vector versus this. And then this is something we also saw in Calculus 3. If we have a vector v given by a, b, and c as its 3 components, we can multiply this vector v by a scalar alpha. By a scalar or a constant, I just mean a real number. And so how this operates is if you do alpha times v, all you do is just multiply each component by alpha, right? So it has the effect of scaling, meaning you're either extending the length of the vector or you're going to be contracting the length of the vector, which I'll look at examples in the next section. So right now I'm just writing things out algebraically. Next, we need to focus on vector arithmetic. So eventually in this class, we'll talk about vector spaces, which is kind of the realm in which vectors operate. And one of the conditions to determine a vector space is you need to make sure that your vectors are closed under addition. So we're going to be caring a lot about vector addition in this class. It's kind of the most intuitive way of defining an algebraic operation between 2 vectors. And it works exactly as you would expect it to. And I guess before going into vector arithmetic, I do want to also talk about matrix notation as well. So in Calculus 3, we mostly use the bracket notation that I introduced on the previous page. In this class, in linear algebra, starting in section 1.3, we're going to be starting to work with matrices, which is kind of like a generalization of a vector. It's kind of like putting a bunch of vectors together to like a single mathematical operation or object. And so in this class, we're generally going to opt for matrix notation. And so how we can write a vector in matrix notation is all summarized via the following equality. And so, I mean, it's exactly as you would expect it to look like, right? So if we have a vector v consisting of the components v1 and v2, in bracket notation, you can write it in matrix notation in the following way. So this is what's called a column vector. It's really what's called like a 2x1 matrix. You can also just call it a column vector, where the two entries of the matrix are just the two components of the vector that you have. And so the virtue of using matrix notation is going to be revealed later. It's kind of what I was getting at before. Matrices are really just a way of combining vectors together. And eventually we're going to be using matrix multiplication. And so when thinking about matrix multiplication, it's much easier to think of vectors in terms of these column vectors or column matrices rather than in bracket notation. We'll see why later on. And so in terms of how do we define addition between two vectors in terms of this matrix notation? So if we have two vectors, there's a typo. I mean, there's going to be typos, folks. I'm not going to lie. There's going to be, this is the first time I'm writing notes for this class. So there's going to be typos, probably several every single week. I'll try and correct them as I go along pretty much. But anyway, so we're going to suppose we have two vectors u and v. If we wanted to add these two vectors together, you just do it component wise, right? So if you do u plus v, it'd be this vector plus this vector. And so you get a new vector out of the sum of these two vectors given by the sum of the components. So the first component is going to be u1 plus v1 here. And then the second component is going to be u2 plus v2. It's going to be this part down here. None of this is probably mind-blowing to you. I mean, again, you've probably seen this in the past, but I feel like I have to review it. Maybe it's been a couple of years since you've done Calculus 3. I don't know. And so just as a basic example, if we wanted to add these two vectors together, you do 2 plus 1 to get 3. You do 3 plus 4 to get 7, right? So you're just adding numbers together. In general, I think linear algebra is a little bit easier than calculus because, I mean, we're not going to be doing a lot of like integrals or derivatives or anything like that. A lot of it's just going to be doing like adding things together and making sure you're like keeping things in order pretty much. Not to say it won't become challenging later on, but I don't know. I always found linear algebra a little bit easier than calculus. That's kind of a side story. It's not relevant to what we're talking about right now. There's like a word for it. I don't remember. Anyways, yeah, so this is addition. The other big operation we care about is scalar multiplication, which I kind of talked about already, but just as an example of what scalar multiplication looks like in terms of this matrix notation is if we have some real number c. So again, this is important to keep note. If you don't know what scalar means, I really just mean a real number. And so if we do some real number c times v, you can write it in the following notation. And so it's just going to be c times both components of our vector, right? So it's going to be c times v1 and then c times v2. And so as a concrete example, if you do 2 times our vector v that we have above, like this vector 2, 3, then you'll do 2 times the vector 2, 3. So you do 2 times 2 to get 4. And then you do 2 times 3 to get 6, right? And then additionally, maybe this doesn't seem that important for now, but when we talk about vector spaces, it's going to be important in the future. We have this idea of the zero vector, which serves as what's called an additive identity. Meaning, if you add the zero vector to any other vector, it's just going to fix that vector. So it doesn't change anything about the vector, which is going to be useful in certain proofs or in demonstrating certain ideas. So the zero vector, as the name implies, is just a vector where all of the components are going to be 0. So in 2 dimensions, you just have 2 components. 3 dimensions, you have 3 components. If you're working in n dimensions, you have n zeros. And so the big point with the zero vector is if you do v plus 0, It's equal to 0 plus v, which is just equal to v itself over again. And then what's also going to be important algebraically is this idea of an additive inverse. So the additive inverse is just going to be the vector itself just multiplied by -1. So -1 is a scalar at the end of the day. So you can take a vector and multiply it by -1. And in doing so, you get a new vector. So if you have v is equal to v1, v2, v3, if you multiply by -1, you get a new vector minus v, obviously minus v1, minus v2, minus v3. If you add these two vectors together, you end up getting the additive identity, which is the 0 vector. So again, it's nothing anything too mind-blowing or anything like that, but it is something that I need to mention moving forward in this class as it's going to show up in the future. Okay, so the first, that was just laying the groundwork in terms of like what's a vector, what do we care about with respect to vectors, so on and so forth. I guess the first sort of idea we're going to be working with are going to be these linear combinations. And this idea of a linear combination is going to show up throughout this class pretty regularly. It's one of the most important ideas in linear algebra. It's really determining like the dimension of the span of your vectors, which we'll talk about a span later in this class, as well as determining whether or not the vectors that you have are linearly independent to one another, i.e., like can they be written as linear combinations of one another. And so this is something I briefly talked about in my Calculus 3 class. Other Calc 3 classes, I don't know if we talk about this very frequently. But what is a linear combination? So we're going to have two vectors, u and v, and then we're going to have two scalars, i.e. real numbers, c and d. And so if you take the scalar multiple, c times v, and you add it to the scalar multiple, d times u, you get what's called a linear combination, right? So the linear combination of these two vectors, or a linear combination of these two vectors, is the following sum. And so the four most important linear combinations, I would say, are the ones that give you the sum of two vectors, the difference of two vectors, the 0 vector, and then like a scalar multiple of your vector v. Right, so you can represent the sum of two vectors as a linear combination by just letting both of the scalars be equal to 1. Again, you can get the difference between two vectors by setting the scalar d equal to -1. You can get the 0 vector by making it so the scalars are both equal to 0. And then you can get a scalar multiple of v back out by just letting the scalar d be equal to 0. And vice versa, right? You can also let c be equal to 0 and then have like d times u or something, which will give you some scalar multiple of u. So these are important examples of linear combinations in this class. And so most of the questions, I'm probably not going to have time to get to the questions until class on Wednesday. But the classes I'm going to be interested in asking initially are going to involve asking what are the possible linear combinations, or like how do you describe the linear combinations of two different vectors, as well as determining whether or not like three vectors end up spanning all of our three. So these are things I'll probably have time to talk about on Wednesday. But before going into that, I need to actually explain like what does it mean to add two vectors together geometrically. We saw what adding two vectors looks like algebraically. You just add things together component-wise. But in this class, it's also going to be important to understand what's going on visually when we add two vectors together. And again, this is something that I talked about briefly in Calculus 3. But again, it's such an important idea that I feel like I should go over it again. And so we're going to suppose, there's like a lot of typos on this part actually. So we're going to suppose we have two different vectors, u and v. And so instead of saying to visualize v plus w, it should be v plus u. And then you're going to follow these three steps. So everywhere you see a w, it should actually be a u. Again, there's going to be mistakes, okay? With the notes, it's going to happen. But to visualize the sum of these two vectors, so we have two vectors u and v. And just to make it clear, So this vector u, it's going 2 units to the right and then 1 unit upwards. So that means this vector is going to be equal to 2, 1. And then this vector v is going 1 unit to the left and then 2 units upwards. So it's going to be the vector minus 1, 2. Just so that we're clear on that. And so we want to ask, what is the sum of these two vectors going to look like? And so you could just add these two vectors together and see what the resulting vector is going to look like. But before we do that, let's just follow this process that's expressed in these following steps here. And so what it's suggesting is that we're going to take these vectors and we're going to add this vector u, and we're going to make it so it starts at the tip or the head of where v is going to be. We're just going to take u and we're going to translate it so that way it starts at v. So it's still going to be going 2 units to the right and then 1 unit up. So this is still the vector u that we have below. And then we can do the exact same thing with v as well. We can take this vector v and then we can translate it so that way it starts at the head of u. And in doing so, we get a parallelogram. Right, so this is a vector that goes 1 unit to the left and then 2 units upwards. So this is still the vector v. And so given any two vectors, u and v, as long as they're not on the same line, you're going to get some sort of parallelogram that has a boundary given by the vectors that we're looking at. And so if you take the sum of these two vectors, what you're going to get is it's going to form the diagonal of this parallelogram, right? So that's why I'm drawing in green. Maybe it's a little hard to see. That's going to be the vector u plus v. Let me zoom in so that way it's less messy. So u plus v is going to be the diagonal of this parallelogram. And you can also see if we were to add the two vectors together, if you did u plus v, you're going to have 2 plus minus 1 is going to give you 1. And then it's going to be 2 plus 1 is going to give you 3. So just making sure we did things correctly, u plus v should be the vector that goes 1 unit to the right and then 3 units up. And that's exactly what we have here, right? So that's the visual way of understanding what the sum of u and v are going to be. You have this parallelogram, and then u plus v is going to be the diagonal. And then it's also worth mentioning that vector addition is commutative, so it doesn't matter the order in which you add vectors together. And so the interpretation doesn't change if you switch the order of v plus u and u plus v. So that's vector addition. Once you understand vector addition, you can understand vector subtraction as well. You should be thinking that vector subtraction is really just vector addition at the end of the day, where you're taking u and adding minus v to it instead of just v itself. That's what's represented in this equation here. So if we wanted to visualize vector subtraction, we just note that u minus v is equal to u plus minus v, which is to say subtraction is just addition at the end of the day. So you can just use the same steps over again. And what we're going to find is that u minus v is going to be the vector that starts at the tip of v and then points as a head to the tip of u. So I guess this will be the last thing I do in class today before ending. And so if we want to figure out what u minus v is, what we can do is we can take v and we can multiply it by minus 1. So if we have that v is equal to the vector minus 1, 2, if we multiply by minus 1, you just multiply both components by minus 1. That'll give you the vector minus v. Let's make it so it's out of the way. So this is going to be vector 1 minus 2. And so now, if we were to add these two vectors together, it would just be the process that we had before, right? You can again form the parallelogram from these two vectors. So this is still going to be minus v, and then this is going to be u here. And now this diagonal is going to be u plus minus v, right? So this is going to be u minus v, which is the same as just saying u plus minus v. And the main point, and maybe there will be some human error here a little bit, is that if I take this arrow and I were to copy it, and then I were to translate it so it started at v, what you'll find is it's going to start at v and it's going to end at u. So these two vectors are the same. I just took this vector and then translated it so that way it started at v. And you see it's going to be the vector that starts at v and it ends where u is going to end. Right, so in understanding vector addition, you can also understand this vector subtraction as well. So in class on Wednesday, we'll get to the good stuff. We'll actually work through problems together as a class. This was all kind of a reminder of what vectors are and what linear combinations are. If you have any questions, I'll stick around for a couple of minutes. Otherwise, enjoy the rest of your first day. I'll see you on Wednesday. Oh yeah, yeah.